What if you could walk through walls? Today, let's talk about an idea. One that powers the most precise microscopes, enables photosynthesis in plants, and defines the upper limit for the world's most powerful computers. Quantum tunneling. Quantum versus classical mechanics. Very, very small. And the very, very big. In classical mechanics, you can use an object's position and momentum to make a prediction about where the object will be later in time. To do this, we use a set of equations called the kinematic equations. In quantum mechanics, you have to remember the Heisenberg uncertainty principle. Because elementary particles are so small, there is an uncertainty as to their position and momentum. Unlike classical mechanics, you can only know one at a time, position or momentum. Instead, physicists use waves to show how likely a particle is to be in a certain place. Using the Schrödinger equation, you can make predictions about the future of a quantum mechanical system. This probability map, where the particle will be in the future, is called the wave function. To use the Schrödinger equation, you have to add up all the different types of energy that a particle has. In classical mechanics, it's like adding potential and kinetic energy to find a total. In quantum mechanics, this total is called the Hamiltonian operator. Once you've added up all the energy in the system, you can make predictions about the future, much the way we can in classical mechanics. With these tools, let's talk quantum tunneling. First, the classical physics setup. A ball in a box. The ball hits the wall of the box and nothing happens. It doesn't have enough energy to get over the wall of the box or tunnel through. Second, the quantum mechanical setup. The particle goes to hit the wall of the box, and there is a wave function associated with its position. Because there is some uncertainty as to where the particle is, there is a solution to its Schrödinger equation that places it outside the box. This means that in some cases, the particle will tunnel through the wall of the box. Remember, this all depends on the wave function. The thicker the wall of the box, the more the wave function decays as it passes through. This means the thinner the wall of the box, the more likely the particle is to quantum tunnel through the wall. Who knows what the future could bring? Years from now, maybe humans could quantum tunnel too. Before we get there though, we have to reconcile the very big with the very small. I'll leave you with one question though. What would you do if you could walk through walls?